Good morning, everyone. A wonderful day here. My name is Robbert Dijkgraaf. I'm the director of the Institute for Advanced Study. And those of you who have perhaps never been here, this is the place that perhaps most famous because Albert Einstein worked here for the last part of his life, 23 years, and many other very famous scientists in the past and the present. It's a place where we're doing research about big questions, how did the universe exist, came to being, what is the world made of, what are elementary particles. And the topic I will be talking about today, which is it's a family talk, so it's great to see many children, but it's also great to see many grown-ups, because often I feel, when the message is kind of directed towards children, it's the perfect way to understand yourself. And I just hope I understand, because we're talking about a very big topic. We're talking about light and color. And of course, it's everywhere around you. But there are many ways, surprising things about light that probably you didn't know yet, and I hope I can tell you a little bit about it. And the first thing, of course, is that there are colors everywhere. You look at the rainbow, you see all the colors. Does somebody know what are the typical colors of the rainbow? Yeah? Purple, indigo, other colors, red, orange, yellow, green, blue. So there are many colors. You can see them here. And it was a terrific discovery, and the person who actually discovered was Isaac Newton a long time ago, that if you have just white light, the light just coming from the sun, that actually you can see all the colors in it. And he did it using what's called a prisma. That's like a little piece of glass like this, which has a funny shape, shaped like a triangle. And then if you have a wide beam of light, it goes through and it gives all these different colors. Now, it's very difficult to do here because you really need sunlight and bright sunlight. And of course, it's a dark room here because you want to see the screen. So just this morning, I took a picture. See, this is me with the prism. So here's the prism, and here I made my little rainbow. But actually, there are many other ways to kind of bring out the colors in light. And actually, just show something. So something you can do all at home. This is just a CD. And let's show that there's colors. Perhaps you already can see, if I kind of turn it around a bit. But let's see it a little bit better. So I need a camera person. Who should I pick? You want to be the camera person? Yeah, I think you're waving. So let me just hook up my camera here. Use the camera. Okay, come here. Okay, you're the camera man here. Okay, so let's see. Can you show us here? See? Do you all see the colors? So let's make a little bit more. Can you? Oh, you see, can you make a rainbow here, right? Yeah. You see it? Just white light. All the colors are there. Perfect. Thank you very much. Thank you very much. You're welcome. And probably I'll need another cameraman later. So let's continue. There we go. And so, of course, one question, how does this can happen? How can light have all these different colors? And perhaps the most important thing to know about light is actually it's a wave. Now, you all know waves in water, but light is also a wave. And does anybody have an idea how you can show that? How would you could show that light is a wave? There's some of the children say, wait, what do you think? A microwave. We'll come to talk about microwaves. But this is some way you can do. So perhaps you've once, if you really look in the sun and you squeeze your eyes, you see little patterns. Sometimes you see little stripes and you see little things. And actually what you see then is very similar to the ripples you see on a pond or if you just have water. And I kind of want to show this. And so I need another person here, another cameraman. I now need a camera girl. You want to be the camera girl? Yes. Okay. So what actually you'll do, just see, why is this not working? not going. Oh, there it's going. Yes. So I need the camera. There we go, yes. Okay, and what I have here is a laser pointer. So you all know a laser pointer, right? So it's like a very can everybody see the little bright light? You can see it? Here on the top here, little piece of red light. Okay, so now I'm going to do, you have to take a picture of that screen. Yeah. If you can see here, you can see whether you're pointing well. Yeah, just if it's right. So now you can see the red dot? Yeah, okay. So now I'm going to shine the laser just on the edge of anything. So let's see what happens. So I'm getting, it's like almost getting an eclipse. So let's see what's happening. Too careful like this. You see the pattern? You see like waves coming off, right? Oh, you aren't, yeah, a little bit. Yeah, great. You see? All kind of ripples that are coming there. You can do that in many ways. And you see this all is coming? You see this, here you can see the waves really well. Thank you very much. I think should a round of applause of our two cameramen. So what we learn from that is that indeed light is a wave, and because it's a wave, it can have various wavelengths. You can have big waves and you can have short waves. And the first thing you have to know that if the waves are small, the light has the color blue, and if the waves are long, the color red. So in some sense, if you look at the different colors, you're just seeing light in different wavelengths. And that actually explains a lot of things. So for instance, if you look again at the rainbow, we see all these different colors, because you can make the wavelength large and smaller, and get these different colors. By the way, there are typically 7 colors in the rainbow. Red, orange, yellow, green, blue, indigo, and violet. And before Newton, there were only 5. But Newton thought that 7 is the perfect number, because there are 7 days in a week. So he had to invent 2 more colors. So he invented indigo, which is like in between purple, violet, and blue, and orange. And if you look at the rainbow, it's a little strip between red and yellow. So that we have 7 colors was because of like symmetry. We had 7 days in the week. We also needed 7 colors. And so you can think of this. So you all know something that is, I hope, that's also a wave. That's sound. Sound is also a wave. And so you can really think as like you have a low sound and a high, that actually that's very similar to light. So in some sense, the rainbow is very similar as the xylophone. You can hear, in some sense, the sounds of light. Only light is oscillating much faster than light. In fact, if you look at the length of the wave of light, it's measured in what's called nanometers, which is a billionth of a meter. So it's incredibly small. But it's not actually that small, because if you compare to something which is really small, like a bacterium, then the wave of light is actually roughly the size of a bacterium. Which means that there's something very funny with this picture. Because if light can only kind of measure things the size of a bacteria, how did I make this picture here? Does anybody have an idea? Well, it's kind of an advanced question. Well, how can you make a picture of bacteria? Can you do that with a microscope, an ordinary microscope? What do you think?
Like we can just see it with a microscope?
No, it's not an ordinary microscope. Because you can think, a microscope can only work with light and it has these kind of big waves. So what else? Somebody else? Yes? Yeah, perfectly. Electron microscope. So that's a whole new lecture, how to make these pictures. But it's good to imagine that if you think what is the size of light, it's roughly the size of a bacterium. So you can never make a picture of something smaller. And actually knowing this already is something very interesting. For instance, there's a question that I think all of you have once asked: why is the sky blue? Why isn't it orange? Or green? Or any other color? White? That actually might make sense. Anybody who has like a one-line answer? No? What do you think? Sorry?
Because of the origin.
Can't understand it. You? Because of light. It has to do with light. And if you want to get one thing out of this lecture, is understanding why the sky is blue. Let's see whether we can understand. So here are two light waves. Here's a red, and here's a blue. They're both in the light, right? They can just get out of it. What you see is white light from the sun. It contains both the red and the blue. Here's a little dust particle or little molecule in the air. So there's a red light ray coming and a blue light coming. But the thing is, so you think these are kind of two collisions. Which collision will be more powerful? The one of the red light or the one of the blue light? Somebody. You.
The red light.
You think the red light, why?
Because it has like longer waves.
Yeah. You?
I just choose the blue light.
You choose the blue light because you know the sky is blue, right?
Yeah.
But think about it. The blue light is kind of really small. The red light is big. So let's kind of see how this molecule looks from the point of view of blue light. Let's just kind of see. So we made the blue light as big as the red light by magnifying. But now actually this little particle becomes much larger. So through the eyes of blue light, there are much more things that you can hit. And actually that's the reason why the sky is blue. The red light just goes past. The blue light actually scatters from it. And in fact, if you understand that, you also know something else. But because now we know why the sunset is red. Why is the sunset red? Think about it. You know, what we've learned, that if light goes through the sky, all the blue light is scattered. So what remains? Yes? The red light passes through, right? So you can see this. So I want to do a little experiment. So I think we might need another cameraman here. Now you can come. So here I have a glass of water. And let me just get my camera running. There we go. And this is like this. So you have to look into, this is the sky. Yeah. So here you can see what you, this is the sun. Can you show me the sun? So we go look like this. Oops, something went wrong. Where's my camera? Here we are. You can see the sun. And now I'm actually going to change the water a little bit. I'm throwing a little bit of milk in it. Oh my God. Perhaps I've done too much. So now let's see what's happening here. Oh, I might have done too much. Can you see anything? Ah, okay. And let me just go through a little bit like this. Perhaps you can see it like this. I can't see it, right? Okay, so we'll do the experiment. We have to do the experiment again. Let me do it later again, because actually it just did a little bit too much milk. But if you do it well, you can actually, I want to see the sun going under. Well, it's difficult to see. Let's go back a bit. Can you see it? Okay, so I'm sorry about that. That's just a little bit of improvisation. If you do this at home, you will actually see that the light becomes red. And one thing you can see, but it's difficult to see perhaps, that the light that kind of scatters off of the milk is a little bit bluish. It's difficult to see, I think, on the camera, but you can see it's a little bit blue light. See it? You see blue light. And if I'd done this more carefully, you would have seen that the sun actually is red. So that's an experiment. It's a nice experiment to do at home, where you actually can see this effect very clearly. So in some sense, the understanding of color is about understanding what light does with materials. And so, for instance, you can ask, why is grass green? What happens there? And actually, it's a complicated story, because grass, that actually has to do with the color of the leaves is made because there are little molecules there that try to absorb the light and make energy out of it. And they do this very well. They take the red light, they take the yellow light, they tell the blue and the purple, but the green light, in some sense, the molecule, the chlorophyll molecule, cannot do anything with. So that kind of bounces back. So the fact that grass is green has to do with the fact that the grass actually is not using the green light, it's reflecting. So if you think green light is the color of nature, it's actually the only color that nature cannot use. So it's like some remainder. All the other parts of the light, if you put a plant under a green lamp, it will not grow. Under a red or blue lamp, it will. So I want to continue, and it's very interesting because we don't stop with the rainbow. So this is a famous moment in science. This is a famous scientist called William Herschel. He was an astronomer. And he does a very interesting experiment here. Here he had a little prism. Here's the rainbow. And he had the idea, let's measure the temperature of light. So he first measures the temperature of light in the blue. He finds, oh, it's like this temperature. And then he moves it to the red. And he discovers that red light is hotter than blue light. That's interesting, right? And then he does something really crazy. He puts the thermometer outside the rainbow. And you know what he discovers there? That it's even hotter outside the rainbow if you go beyond the red. So, well, you can read. This is the discovery of a new thing. It's called infrared light. There is light that you cannot see, but you can feel. It's the light that actually comes from warmth. So, for instance, if you, and I'll come back to it in a moment, if something is very hot, you can feel it. You feel the radiation. But if your eyes could see infrared, you could actually see things that are hot. So actually, it's very obvious. You think about it, I told you, what is light? Well, it's like this little xylophone. That's the visible light that we can see. But think about, can we have more sounds than the ones that you can play on a xylophone? For instance, if you want to play more sounds, what would you pick? What kind of instrument? Anybody? Yes? Yeah, piano. So if you take a grand piano, then certainly there's a whole range of sounds. Very low and very high. And so the great thing is that it's exactly the same that's happening with light. What you see in a rainbow is just this little part of the piano. It continues all the way to the left and all the way to the right. And so there's much more to be discovered in light than just the things that we can see. And we see in a moment that there are all kinds of animals that make use of that. So for instance, if you go beyond the red, which means wavelength even longer than the wavelength of visible red light, you get much bigger things. So you should think of the rainbow. This is the little part we can see. But if you're a scientist, you can go all the way here and all the way here. There's much more light than we can see. It's like we are looking through a little slit to the world. And actually, I want to tell you about this. In fact, the technical thing, I don't have time to explain this, is that all of that light is called electromagnetic radiation. So it has to do with electricity and magnetism and how they are connected with each other. And in fact, there are beautiful equations that describe all of this. So that's this equation. This is kind of a funny t-shirt that you can actually buy. So light is the solution to these mathematical equations. And the person who discovered this 150 years ago was James Clerk Maxwell. He was a Scottish physicist. And it's important to know that for Einstein's work, Maxwell was absolutely important. In his private office, Einstein had a portrait of Maxwell because he really unified a whole range of activities, whole kind of phenomena, showing it's all basically the same thing. It's all light in different forms and shapes. So for instance, some of you might have seen infrared cameras. If you have an infrared camera, you can actually detect things that are warm. Now you often see this in spy movies and in warfare, yes? Snakes have that vision, indeed. Snakes have little eyes that can see the infrared. But we can feel the infrared. No? You can just feel where things are hot or not. But you can't see it. So we have special cameras. So this is a funny thing because somebody kind of hides his hands under a plastic bag. But the infrared camera can just go through it and can see it. Oh, you see infrared cameras are very, very places. So now, in fact, if you want to, you can buy an infrared camera to take pictures. And many people will do this. So these are pictures that look very strange because they're not made with visible light, they're made with infrared light. And you can actually see that the trees and the grass all is very bright. So why would it be very bright in infrared? Why do you think? Yes?
Because it's very hot and red is like hotter than blue, so it might be a little
Yeah, it's
brighter.
because it's a little bit warm. It also has to do, of course, I told you, why is things are green? Because the green light gets reflected. So we see here that trees and everything, they also refract the infrared light. So that's why it looks like these trees are all covered in snow. So if you could see in the infrared, that's how nature would look like. I think that would be very beautiful, right? To walk into the woods, because it would kind of be very bright. And we can show this. So we can continue, in fact. So this is for infrared light, microwaves. Perhaps all of you have a microwave at home. It's the same as light, only the wavelength is now even bigger. For a microwave, it's roughly like a centimeter. So you remember, visible light is the size of a bacteria. For microwave, the light, the radiation, has the size of 1 to a couple of centimeters. So something that you can really see. And you can go on, like for instance radio. Radio waves that you can pick up is also light. It's electromagnetic radiation. However, now the wavelengths are much bigger. They could be meters, even hundreds of meters. Even bigger. In fact, they could be so big that they kind of go around the Earth. And one of the nice things is that, the Earth itself is basically like a big radio. Did any of you ever listen to the Earth? So I think we can do now. Let's hear. I hope the sound is coming. Dario, can you turn it up? No, it's not working, I think. Okay, next time. Yeah, sorry about it. So we can have wavelengths that are redder and redder and redder, that are longer and longer and longer. We can also go to the other direction. If we go to wavelengths that are smaller than blue, does somebody know what you get if you get more bluer than blue? It's already written there. Ultraviolet. It's going beyond the purple. And ultraviolet light is very dangerous, we know this, right? That's something that's why we kind of use UV protection when we go sunbathing. And why does somebody have an idea why ultraviolet light is more dangerous than visible light? Yes, there in the back. Almost right. It's smaller wavelength. So now you know it's smaller wavelength. Why do you think it's more dangerous? It goes faster and it can hit. Think about the sky. Why was the sky blue? Because blue light was smaller and it would kind of hit head-on with the dust particles in the molecules. So ultraviolet is even smaller. So it can hit molecules. It can actually destroy the molecules in your skin and actually and in your body. And that's why it's dangerous. If the wavelengths are longer, like in radio, they're not dangerous. But if they're smaller, then actually they can be more powerful. They can actually destroy pieces in you. And this goes on. For instance, if you... Oh, by the way, we can't show infrared light and we can't show ultraviolet light. But some of you have perhaps seen black light. If you go to some things that you don't see the light, but suddenly your T-shirt lights up or something. That actually is ultraviolet light. You can buy a lamp that radiates ultraviolet light. If you make the light even smaller, you get X-rays. So our X-rays, we don't have X-ray vision. We can use it, when we go to take X-rays at the dentist or at the hospital. And so I'm just asking, what do you think? Are X-ray dangerous or not? Yes?
Yes.
Why would they be dangerous? Now tell me why.
Because the UV light, like the UV, it's like, it might be damaging your skin a little.
Yeah, it might be even more damaging, right? Because it's even smaller. So it can even hit the atoms. It can really destroy the atoms in your body. And so that when you take an X-ray picture, you have to take it for a very brief moment, because otherwise, it's just for a fraction of a second. And there's something even more dangerous than X-rays. If somebody knows what if you go, yeah, in the back with the blue. Sorry? Gamma rays, exactly. So there's something called gamma rays, and gamma rays are, the way to produce them is, for instance, with a nuclear explosion, or, stars, exploding stars in the sky. And the gamma rays are so powerful, they not can only break molecules or atoms, they can even break the nucleus of an atom. So they can actually kind of make things radioactive, change really the nature. And so all these different kinds of light we can use. So we'll come in a moment to animals, but like astronomers. Here you see a picture of the moon. And these are pictures of the moon taken with X-rays and with infrared. So like scientists are using all these different forms of light. For instance, here you have the galaxy. The galaxy, as we can see it with our own eyes, but here using X-rays, using radio waves, using infrared. Often if you see astronomers, they use the whole grand piano, while we human beings are always playing our little xylophone. That's the only thing we see just now at this moment. But there's another thing I want to ask you. So we all know the rainbow. It goes from red to violet. But you all must have thought at one moment there's something very funny. You can glue the two ends of the rainbow together. Did you ever try this? There's a thing called the color circle. You can go from red to orange to green to what's called cyan to blue to purple, violet, and then you go back to red. Why? This is really crazy. Because, on the one hand, this is the very long wavelength, and this is the very short wavelength. Why are they tied together? To understand that, actually, we have to not think about the physics. Up to now, we're just talking about physics. So now we have to move into biology. Because we have to think about how our human eye works. And our eye is really quite an amazing object. So, in fact, this is a little picture of your eye. Light falls into the eye. You make a little screen. You think you're looking at me now, but you're not. You're looking at the back of your eye. There's two little screens, and you're looking at these screens. You're not looking at me. You just see this little image. If you squeeze your eye a little bit, then you see the image is changing. So on the back side of your eye, you have all these cells here that are very sensitive, and they absorb the light, and they give a little electric signal that then goes to your brain. And if you look, you can again take the electron scanning microscope, and here you can see. So these are these cells that actually they look like little fibers, and they react whenever the little light ray falls on top of them. They just produce a microscopic electrical current that goes to your brain. And there are two kinds of cells, rods, that you use at night, but the thing I want to talk about are called cones. And these cones, and you can see them here in this picture, they come in three kinds. There are red cones, there are green cones, and there are blue cones. So if you look at your eye, you can actually see sensitivity for three different colors. Here you see the rainbow. One is sensitive to the red, one is sensitive more or less to the green, and the third is sensitive to the blue. And so if you look at your eye, with your eye, you're actually seeing three pictures at the same time. Your brain gets input from a red picture, a green picture, a blue picture, and then it all gets processed, and you say, hey, I have a color picture. Your brain is doing this continuously. Unless you are in the middle of the night, when there's very little light, then actually this stops, and then the other system takes over, which is a black and white system. Did any of you ever try to look when you wake up in the middle of the night and try to see a color?
I tried it.
Did you manage?
No, but it was like all black, and I couldn't even see. I was like, I'm blindfolded, and anybody else just put something on my eyes, and I couldn't see anything.
But for instance, tonight there's a really big full moon. You can go outside in the moon, and you can see things. But you don't see colors, right? You can't see this is a blue shirt or a red shirt, you don't see. But now we can see. So at this moment, if you look at the colors around you, just think about what your brain is doing. It's continuously combining these three pictures. So I want you to understand one thing, that actually color is three-dimensional. You see color using these three components together. And so that's why if you combine the colors, you can actually get different colors. So I would love to do this like in a real experiment. It's kind of difficult to do. But for instance, if you have the red and the green at the same time, so that's something you can try at home too, have a red and a green light. If they fall on top of each other, they produce yellow. If you have blue and green, they produce this kind of cyan. And this called magenta is produced by purple, basically, by combining red and blue. And in fact, you see this everywhere around. I think, well, let's see whether we can do it. Yeah, I want one of the children to come here. Let's see whether we can do it again with the camera. No, I don't think we get it. Can you come? So you want just to tell me what you see if you really look up close at the screen.
I see lines and squares.
Look closer. Do you see color? You're looking at the white.
Yes.
What colors do you see?
The rainbow.
The rainbow. Well, look very careful. See the rainbow? All the colors of the rainbow or not?
I see green.
Green.
I see purple. I see cyan.
Do you see blue?
Yeah.
Yeah. So actually, I think you can do this all at home with any of your screen. You see this. This is just a close-up picture of a computer screen or a television screen. And you see the different colors there, the three colors, red, green, and blue. In fact, this is how the screen looks up very close up. You see red, green, and blue. So that actually is how colors are made on the screen, exactly in the same way as it happens in our eyes. So one part of our eye picks up all the red, the other one picks up the green, and the third one picks up the blue. So if you think about colors, you really can think of them as 3 dimensions. So because you combine red, green, and blue. So think about it as you can go the length, the breadth, and the width. So there are 3 dimensions in our colors. And this is special for human beings. We can see color in 3 dimensions. And I want to ask you, why do we see colors? Actually, it looks like such a complicated deal. Why are we going to do this? What's the advantage of seeing color? Somebody here. Why would we see color? Let's look at this thing. Somebody sees something here, which is, this is like an average day in the jungle. Does it look okay? Does it look okay? Why not? It's black and white. Well, okay, so we go to easy system. Forget about color vision. Just one, much more simple. Just black and white. Would there be any advantage to see color? No. No? What do you think?
Yes.
Why?
Yes. Let's see.
What do you see here, what you don't see in the other one?
The
The panther, yeah. So this is just the last moment I saw before I was eaten up. So then evolution said, let's produce color, right? Because you can see much more.
So color is meant to notice things?
Yeah.
Like it's easier to notice?
Think about the jungle. Everything is green, except like flowers, animals. So actually seeing color is very useful. And that's why most animals actually can see color. So perhaps all of you know, are there anybody who have a dog or a cat? Does anybody ever wondered how a dog or a cat, do you have a dog or a cat?
I have a dog and
Dog and a cat. So how would they look at the world? You think they can see the same colors as we are?
No.
You don't know? Oh, actually, this is something you can investigate. Do you know?
They can only see red and yellow.
Wow, more or less, yes. They can see 2 colors. So humans can see the rainbow like this because we have 3-dimensional colors, red, green, and blue. You're more or less right. Yellow and blue are the 2 things that dogs can see. So if you would produce a television screen for dogs, you only need 2 instead of 3 different colors. So, dogs look at the world in a kind of look at a simple. So, now we see this kind of very cute puppy, but no, dogs see this. It's a little bit washed out, There's not that many colors. You think there are animals who can see more colors than human beings? Yes? Oh, we come to the shrimp in a moment. We come to the shrimp in a moment. Somebody else. Are there? Yeah, in the back with the red sweater. Yeah. Scream. Birds, yes. I come to birds in a moment. You. Snakes. Yes. Very good. We already talked about snakes can see infrared even, yes? Yeah? Sorry? Dragonfly, very good. Insects. So this effect, in the animal kingdom, there are many more colors than we think. So this is our eye, so it's sensitive to the three colors, basically the yellow, the green, and the blue. Insects can also see three-dimensional color, but they use basically green and blue, and then they use ultraviolet. So they have a third color, that's something we cannot see, but they can't really see the red. And birds are amazing because they have four-dimensional vision. They can see the red, the blue, and the green and the blue, and also ultraviolet. So birds have a much more beautiful view of the world. It's very difficult for us to imagine because our eye can only think about three colors. So if you're a bee, so again, the bees can also see the ultraviolet. We can't see. So if a bee looks at a flower, they see much more. For instance, these flowers are just yellow for us. But it turns out that in the ultraviolet, the heart of the flower lights up. So if a bees want to find, so why is this important for a bee to actually know where the center of the flower is? Yes, you. For the nectar, yeah. So now we would say, well, where do I go, where do I go? But if you see this, it's like a landing pad for like a helicopter, It won't exactly know where to go. So I always feel this is a little bit like, some of you have seen the movie Avatar, where you see all these kind of beautiful colors, and like, well, that's probably a little bit like insects must see the world, The flowers are much more beautiful than ours. And you see this very dull flower, again, it lights up. And for birds, it must be even more amazing. So for instance, since birds see in four dimensions, so this is the color. This bird looks just black to us. But it turns out in the ultraviolet, there's all kind of colors there. So for birds, they look even more colorful than we think they are. And so you can ask, well, is it possible for us to see in four dimensions? So I actually know a physics colleague of mine who's trying to do this. He has he won't tell me how. I think he says it's secret. But so perhaps in a few years you will read that you can buy a kind of something like a Google Glass that makes you see colors in four dimensions. And if this happens, then just remember you first heard it here. Four-dimensional color. And then 3D, that's kind of so silly. But there's an animal, and it was already mentioned, a shrimp, and I just would mention, because it's like he is the absolute king, emperor of color vision. And that's the Mantis Shrimp. So here he is. And the Mantis Shrimp can see 16 different colors. So this is not about how many different colors we can see. Because with red, green, and blue, we can make everything, we think. But then there's all kind of other different. So you see he has beautiful eyes. In fact, the eye is very complicated. He is looking at the camera. There's these three little slits. And it is a different eye than ours. It has all these different kind of little cameras. And there are 16 different cameras. So here again is the rainbow. Here is our eye, red, green, and blue. Our computer screen has these red, green, and blue dots. If you be a Mantis shrimp, you have 16 different kinds of cells in your eye. And just imagine that you have to buy, that this guy has to buy a computer screen, just has to have a very refined. In fact, there are even things in the shrimp's eye, I won't be talking about here today, but some of you might have heard of polarization, of polarites. So sometimes you have sunglasses that the reflection of the light from the wave, takes it out. That's because light can basically oscillate in two different directions. We are totally insensitive to that, but the Mantis shrimp is also sensitive to that. So this is like the full, all the options that you can possibly, evolution can possibly give to an eye, all in this little creature. Now, of course, the Mantis shrimps are not conquering the world, so I'm not quite sure why he needs that very complicated eye, but it's kind of pretty amazing. But I want to take one step further. So we have seen there is light is a wave. It's out there. It comes to our eye, it's being processed, and it's sent to our brain. But you think this, anybody feels kind of squeezy looking at this picture? What's happening with the picture? Yes? What's happening with the picture?
Oh,
yeah?
Oh, it looks like it's
It's moving, right? But you think it's moving? You don't think it, but you think it's not moving. This is just a picture. But your brain thinks it's moving, right? This is another famous one. So these are strips of gray, but honestly, it looks like, it's like kind of, don't you feel that the gray here gets a little bit darker and then it gets a bit lighter here? It feels like somebody has kind of enhanced, a little bit the contrast here. It's not. It's something, your brain is like photoshopping the image. This is another famous one. You see these white dots at the intersection. Actually, at each intersection there's a white dot, but I think, at least for me, I can't see all of them at the same time. Some are black and some are white and some are black. They're all white. So your brain is fooling with you. In fact, you thought light was a wave, and then I told you light is something in your eye that's being picked up. It's not. It's what your brain makes of it. And so now we're going to see very different things. For instance, you see this checkerboard. You see this one is gray and this is white, right? A and B. Everybody agrees? Okay, the question is, and it's kind of a trick question, which is darker, A or B? So who thinks A is darker? Who thinks B is darker? Who thinks A and B are the same? Yeah. In fact, they are, and here you can see it. What? What's happening here? It's crazy, right? You see there, it's really the same color. Your brain is fooling you. Your brain fools you all the time. For instance, just to say that this is a little picture of a screen. It's like very, very vague and unclear. I'll make it a little bit clearer. Here it is. And I cut it in little squares. Well, they roughly look like the same color, right? If I would tell you this is just a screen and there's light on the screen, so it's a little bit shady here and a bit lighter over there, it's fine. If I cut these little squares and I scramble them, I get this. So all these different colors are in this picture. Your mind might say, well, it's all roughly the same. It's not. Look at the differences. How dark and how light and how blue and how orange. They're all over here. Well, perhaps some of you remember a few years ago there was a controversy about this picture. Remember this picture? And there was a controversy because this was a picture of a dress. And the question is it a blue dress with black ribbons or is it a white dress with gold ribbons? No, it's a dress. It's a dress. So let's do, again, so some of you have been through this. Blue-black. Who says blue-black? Who sees white-gold? Okay, you see white-gold. Okay. So basically, these are the two options, right? It's either white-gold or it's blue-black. But your eye is kind of uncertain. I mean, I find it very difficult. Once you see once, it's very difficult to go back. So this is the fabric. And it's basically what do you tell your brain to see? For instance, I can say, well, this is a piece of fabric. It's a piece of this fabric, which is white and gold, but it's just in a shade. If you're a painter, you paint a white sheet in the shade, you might see some bluish there. Actually, it's reflection of the sky. That's one way to look at it. You can also say, no. It's a piece of black and blue, which is in the sun. And here you have both. It's really confusing. And so what we see as a color is very much in our mind. It has nothing to do with what our eye sees. It's really how we interpret. In fact, the answer to the question, is actually it was a blue-black dress. But there were so many people who loved the white and gold dress, and then the same company also started to make a white and gold dress. So now you can have both. Here's another example. So here are 3 pictures of a girl. And you see the eye. Look at the left eye. So I'm almost claiming that this girl her left eye is almost that color, right? Here it's like yellowish, and here it's reddish. You agree? Yeah. So we have a girl with a blue eye, a yellow eye, and a red eye. It's not true. All three eyes are gray. If you just take this away and you just look at this thing here is exactly this color. So your mind makes the eye red, or green, or yellow. And there are many ways in which this happens. And so color is actually something that's very much in our mind. And actually, I want to say something about somebody who really investigated this, and this is a kind of an American hero. It's Edmund Lance. He was the inventor of the Polaroid Corporation. So Polaroid pictures were pictures that you could, make a picture, and then in the old days, and you have like instantaneous, a physical thing which you could take out. And he was really very curious to understand how light works. And he did lots of experiments. So here you see here, he created this kind of paintings that he called like Mondrian, from the famous Dutch painter. And he had cameras looking at the paint, and he did an experiment, and I want to show you the experiment because it's a really interesting experiment. He took a picture of this. This is a still life. So let's look at it. Can everybody see all the different colors in the picture? There's green, there's red, there's yellow, there's like blue, there's purple. Here's another version of the picture. It's not the same, but does everybody see the kind of blue-green here? And this is like light blue, right? And this looks yellow, doesn't it? No? Orange, yeah. That's like the orange, yeah, orange. And the yellow, you can still see it here, right? Not very clear, but it's still there. Pink, okay. So the amazing thing is that this picture is made with only two colors, red and black. There's no green, there's no blue, there's no yellow, there's only gray. If you think that this green is still here, it's not, it's just gray. But your eye your brain makes you think you see the colors. So you can see colors that aren't there. In fact, somebody didn't believe it and said, let's try to copy this thing with paint and only using red, white, and black. And in fact, they created this painting. So it's only gray. This looks like greenish to me, and this looks a little bit kind of yellowish to me, but it's not. You can see colors that aren't there. That's just a very powerful property of our brain. So before I finish, I want to tell you one more story, because we've shown about the light around us. So what did we learn? We learned, one, that light was a wave. It can have short wavelength and long wavelengths. The short wavelengths are blue, the long wavelengths are red. Then we look with our eyes, and in our eyes we combine the three colors. And then the whole thing gets processed in our brain, and then lots of other stuff happens. And we've also learned that some animals can do much more than we can. But now I want to kind of end with kind of looking a little bit at the sky. And I want to ask the question, when was the first light created in the universe? When? Has there always been light? Let's first ask a question about the light of the sun. How long do you think that does it take for the light in the sun to be produced? Do you know? 8 minutes. Can somebody say something about the 8 minutes? Why does he say 8 minutes? What do you mean exactly with the 8 minutes? Yes? Exactly. It takes 8.5 minutes from the light of what is produced at the surface of the sun to come here on Earth, and that you see it in your eye. But the light is produced inside the sun in some kind of a nuclear reaction, in the heart, in the core of the sun. And it takes a long time for the light to get out. Did you know it takes hundreds of thousands of years to do so? Roughly 100,000 years for a light particle, when it's created in the core of the sun, to travel through this very thick object and escape, and then in the last 8.5 minutes it travels to us. So if you think about the light of the sun, there are two parts. It's produced in the center, then it has to kind of try to get out, and then it actually escapes, and then you can see it. So the question is actually, when was the first light produced in the universe? In the same way as it's now produced in the sun. Yes, in the back. With the Big Bang. Almost. Almost. In fact, a little bit later, and we'll tell you in a moment, but I think the interesting thing that you should all know is when that light was first observed. And it's a beautiful story. It actually happened here in New Jersey. There were two basically radio engineers, Penzias and Wilson, who in 1965, so that's 51 years ago, we had a big celebration about this last year, they had this kind of telescope, and it was being used to have communications with kind of satellites, and they had a funny noise in it. I wanted to play the music, but I think it's probably not working again. Is it working? No, it's not. Okay, well, we'll have to, but you will just hear bzzz, like just a boring noise. And they couldn't understand what was happening. And so there were two young engineers, and somebody told them, well, just make sure that this kind of, this disturbing noise is removed. And they did many things. For instance, there were a group of pigeons who had built a nest inside. And they covered the whole telescope, what in the final article I think is mentioned as an organic condensator. So I mean, there was a lot of kind of pigeon droppings all over. They removed that. And they still had this kind of little noise in this telescope. And what turns out that we're listening to was actually the sound from the universe. The first light that was produced. And in fact, that first light was produced roughly 400,000 years after the Big Bang. So you have to think about, just after the Big Bang, there was a lot of material, but it was squeezed together. Very similar as like inside the sun. Now you might think that you perhaps read that the sun is a big, gas, sphere of gas. It's not. It's very solid. It's very heavy, very much compressed, much more compressed than the Earth. So it's very dense material. And what happened with the Big Bang, it started to expand, the universe started to expand, and after roughly 380,000 years, it became translucent. The light could kind of escape. And that light actually, so this was what astronomers called first light. And it's a beautiful term, but it's really true. The first light was produced 380,000 years after the Big Bang, and the Big Bang itself is 13.8 billion years ago. And that light, when that finally escaped, it was very hot. So this was like very, very short wavelength. But then the universe started to expand, expand, expand. You can imagine what happens if the universe expands. What happens with the light? What do you think would happen with the light? Somebody, what will happen if everything expands? Think about the waves of the light. So what will happen with them? Yes?
They will get straight.
They get straightened out. So what happens with the wavelength? If it was short first, it gets?
Stretched.
Gets longer.
Yep, it gets stretched.
So for instance, if light at some point was purple, and you would wait a little bit, what would be the color of the light then? After just wait a few billion years. Yeah, like bluish, or perhaps green, or yellow, or red, and it goes on and on and on. So it started with perhaps it was even like gamma rays, but then it gets stretched and stretched and stretched, and became red light, then it became infrared light, and then it became even longer than infrared light. So now it's a little test, if anybody paid attention. If you go beyond infrared, what would you get? Somebody remembers? Beyond infrared. Yes? Microwaves. Yes, microwaves. In fact, the universe is so big now that it's microwave radiation. So if your eyes could see microwaves, not only it would be interesting if you kind of put a little cup of chocolate milk inside it, you could actually see it. But in fact, if your eyes could see microwaves and you could look at the sky, this is what you would more or less see. This is the light that's there. And one thing that's very interesting, if you take a television screen, an old-fashioned television with an antenna that can pick up these waves, then you can actually pick up that signal. and you get like this little static. And roughly 1% of the static are little light rays from the very beginning hitting actually your television screen. And you can actually measure them. So quite remarkable, these lights are over there. And so if you think about the evolution of the universe, you can think it was a big bang, and then after this 400,000 years, the first light was emitted, and it travels all the way here. Now, the point was that nobody was around to see that first light. No, it was like, there weren't no stars, there weren't even atoms, there weren't no galaxies, nothing. We had to wait 13.8 billion years now with our satellites that we can measure this. And even on planet Earth, who you think would be the first animal or whatever who saw light? Who? What kind of thing would be the first thing to see light? You think you know it? Bacteria. Bacteria? Why?
Because that was the first thing.
Why do they use light? Do they have an eye? Does a bacterium have an eye? No. So what do you mean it saw light? I think you're right. It's a good answer. But why would a bacterium do something with light? Yes, you? Exactly, to produce energy. So actually that's something that we like plants still use, right? They absorb light to produce energy. And in some sense, what our eyes are doing the same thing to produce energy. So perhaps there was a bacteria, like perhaps 4 billion years ago, who was the first person to see light. But there was no human being then. So nobody of us was around when the first light was detected. But there's something else than light, and that's the last thing I want to show you. Light is a wave, but it's another kind of wave. And it's called the gravitational wave. It's actually a little wave in space itself. Now this is something completely different. But it's exciting, you should know about it, first of all, because the person who told us that these things are there is Albert Einstein. And he predicted these gravitational waves more than 100 years ago. And they are there. They actually will be produced in the Big Bang, they will be produced in the sky. But there's no bacteria that can see it. Nobody, no animal, no plant has an eye that's so sensitive that it can measure these gravitational waves. But human beings. So the last few decades, human beings have producing eyes that can see gravitational waves. And in fact, just as we have a left eye and a right eye, they produce two of these kind of artificial eyes that can detect gravitational waves. And these are a few miles long, and they're incredibly sensitive. They can measure something. If you write it in decimal notation, it's 1 in 10 to the 22. So it's like 0.00022 zeros 1. The weakest signal, and it's called LIGO, it's a gravitational wave detector. And last year, for the first time, they detected a gravitational wave. And you were all around. There's nobody here who's younger than like 1 year. So you were all around when the first gravitational light was detected. And in fact, what they saw, here you see the signal, they saw two black holes colliding. So everything I was telling you about today, about light and the properties of light, how we detect, the whole story, you can also tell about gravitational waves, with one big difference, that actually you were present when this kind of happened. So that's very exciting. And it means that human beings are even cleverer than a Mantis shrimp, because the Mantis shrimp could see 16 different versions of light. But this gravitational version only we can see. So thank you very much for being here.